Our last video for this section in the textbook is about scientific notation. And in the sciences, we often use really, really, really big numbers or really, really, really small numbers. But even the small numbers take up a lot of space on your paper to write, or a lot of space in the document to type. For example, um, computers can do calculations in the frame of 33 trillion per second, right? So just incredible computing speed. It's a big number. It takes up a lot of space on the paper. And so we have a way to condense this number into a smaller area. And again, we call this scientific notation. And so what I'm going to do is I'm going to write it out. But I'm not going to say anything. Sometimes I like to teach this by just having you observe what I do and how I think about it. So I always tell my students, just pause and stare at what I did and just sort of see if you can make sense or figure out what happened there. What we do is we condense our number and we use a power of 10. We're familiar with those, a power of 10. You know that when you take any number, say 4, and multiply it by 10, it turns into 40. It moves the decimal over one spot. Or if you take that same 4 and you multiply it by 100, it's 400. Remember, 100 is 10 to the second power. Or you could take 4 times 1,000, which is the same as 10 to the third power, and you would move that decimal point over from here to here, which is 3 spots. It would add 3 zeros. And so notice that this is starting to take up a lot more space on the paper. It's longer. This is still just the starting number 4. But we wrote it as a multiplication problem. 4 times 10 to the third is equal to 4,000. As this number gets longer and longer, this will stay the same length. I could say 4 times 10 to the 8th, and it's going to be 4, 1, 2, 3, 4, 5, 6, 7, 8. Right now we're getting a really big number, 400 million. And so scientific notation, the way we write it is always going to be like this. You have a single digit, 1 through 9. Again, it's going to be a single digit, followed by, if you need it, a decimal point and other numbers, non-zero numbers, really until you get to your last non-zero numbers. And then you drop off any other zeros, like these zeros. The point of it is to eliminate zeros. So we eliminate those. And then times 10, and it's going to be some exponent like that. And so we use a positive exponent here because what this is really saying is we really need to multiply 3.3 times a really big power of 10, one with 16 zeros. And so the actual value of this statement is this thing, right? The actual value needs this decimal point that we see right here to be back here at the end. And it would move that decimal point all the way back here. And so that's how we condense it. Now, we can also have really, really small numbers. Let's say we have this. I'm going to look at a different example. And we're going to say 0.0000000. Let's go 405. And we are going to write this in scientific notation. Now, remember, the rule says we are going to have one single number, 1 through 9, a decimal point if we need it, and any other numbers if we needed, right? So this is like if needed. And then we have to write that times 10 to some exponent. So in this case, we want our decimal point to be where? we want one number before the decimal point. So we're going to have our number be there and our decimal point come right after it. So we're going to move this decimal point from here all the way down to there. So we're going to jump 1, 2, 3, 4, 5, 6 places. So this is now 6 places, and it moved to the right. So we're going to write 4.05. So we want the 0 and the 5 times 10, but what is this exponent going to be? Let me show you. I'm going to tell you first, then I'll give you an explanation of why. It is going to be -6. Negative exponents make numbers really small. I'll give you maybe a better example to illustrate this. What if we just had to do this? Think about that number right there, 0.003. What is that as a fraction? I'll ask you. 3/1000. Okay. And if we then write that as 3/1000 as base 10 is 10 to the third. Okay. Now let's start comparing this to scientific notation. If I wanted to write it in scientific notation, I would move that decimal 3 spots to the right. 3 times 10, and it would be to the negative third, which is what I had shown you up there. You use a negative exponent. When you start with a decimal, really small decimal, and we're moving that decimal to the right. And notice the different ways in which I approach this problem. Here, we see that we've got this 10 to the third on the bottom, and here we write it as 10 to the negative third. Well, there's a property of exponents, negative exponents, that says any number, we'll just call it x, to the negative exponent, I'll call it n, is equal to 1 over that number to the positive n. So negative exponents, what they do is they take the base, and they are really saying it belongs in the denominator. So 10 to the negative third is the same thing as 1 over 10 to the third. And you can see that here when you divide by that 1,000, it makes your decimal small. And so this is equivalent to 3 times 10 to the negative third. So this is how we deal with negative exponents. And so with scientific notation, it's really beneficial. The one thing you have to remember then is the really small numbers like this, when we write them in scientific notation, get negative exponents. So it's time for you to try some of these. What we'll do is I'll give you a number, and you see if you can put it in scientific notation, and then we'll also go backward. So here is the first number. We're going to write this in scientific notation. Go ahead and give that one a shot. So if you tried this, you would know that the decimal starts here, and we need to move it back, all the way into that location right there. It's got to be right before or right after that 2. So we'll write it as 2.77. We can drop all those zeros times 10, and we moved our decimal, if we count by threes, 3, 6, 9, 10 to the 9th. And it's going to be a positive 9 because this was a really big number, and we shrank it. And if we re-multiplied all this out, it would move our decimal point all the way back to the end. So 2.77 times 10 to the 9th. How about this? One more here. 0.000006048. Go ahead and try that in scientific notation. And so with this one, we're moving our decimal point all the way back to immediately after the 6. So we'll have the 6, then we'll put our decimal point, and then we'll keep those numbers. 6.048 times 10. How many 10s do we need? Well, we're moving it 1, 2, 3, 4, 5, 6, 7. I don't know why that changed to a line, but it was 7 spots back to the left. And so this is -7. Why is it -7? because it's really, or also thought of as 1 over 10 times 1 over 10 to the 7th power, which would, again, divide by that big power of 10. It would move that decimal back to the left. But this is how we write it in traditional scientific notation. And so the last thing I'll give you is I'll write the number in scientific notation and see if you can then put that back in its standard numerical form. So let's go with 9.14 times 10 to the negative 7th and 41290. But both, oh, sorry, I gave you the wrong way. I have to change that. I gave you the regular number there. Let's go with 8.05 times 10 to the 6th. So put both of those back in their normal numerical form. The first one, 9.14 times 10 to the 7th, we would take that decimal point and we would move it 7 places back to the left. So the first spot jumps to 9, which means we need to put 6 more zeros in front of that 9. So decimal point, 1, 2, 3, 4, 5, 6, 9, 1, 4. Double check it. 1, 2, 3, 4, 5, 6, 7 spots. So there is our actual numerical value of this number. This one has a positive exponent, so we move it 6 spots back to the right. So 8, 0, 5. There's my first 2. And then I need 4 more zeros. 8,050,000. And so that is scientific notation. Again, we got away from percentages a little bit, but again, it's related to this idea of working with decimals.